record.
It sounded like away or something. The class I'm checking there today. Like, sorry.
Okay, wait, let me pull this over to the other tab.
Did you guys update the announcements too?
Yeah.
Okay. Well, I'll
All
start
right, let
and
me
then-
share screen.
Oh, thanks.
Let me make this small.
And we're recording?
Yeah.
Okay, cool.
But then I realized that I didn't write that website. And played it instead on the actual, the website that actually made the movie, which was, I can't remember the name. The first one,
Okay, it's 3:10, so let's get started. Welcome to Wednesday, the first class before spring break, which is pretty exciting. Yeah. Not the last class, just before spring break.
No, the last class.
Yeah.
I thought you said first.
Oh, sorry. I meant last if I said first. It's okay. All right. Anyway, some announcements for today. Don't forget your project proposals are due this Friday, and those need to be latex. And so we talked about latex last week. So make sure to get those in. Yeah, so then you don't have to think about it over spring break. Yeah, so what we're going to be going over today is AstroPy. So I think between NumPy, Matplotlib, being my favorite packages in Python, this is probably my third favorite package. It's super powerful. It's really cool. I use it all the time for research as well as homeworks. And I think after what we show you what it can do today, you'll also be big fans. So this library is designed to make astronomy research easier. But even if you're not an astronomy major, you're like some STEM major, this package is still really, really useful. So there's lots of packages within AstroPy itself, and we'll show you about how to import those and use those. But you might have to install it by running pip install AstroPy in your terminal. So yeah, you might want to try that before running these AstroPy commands. Otherwise, you might get some errors. Yeah, so what is AstroPy? What does it actually do? So I want you to imagine a world where you never needed to perform another unit conversion by hand ever again. Sounds pretty cool, pretty great. I know I'm so sick of that in problem sets where it's giving you values in hours and it's convert to seconds or whatever. Annoying stuff. But AstroPy directly deals with that. So you never have to do unit conversions by hand. You can assign units to variables and AstroPy will keep track of them. So how this kind of works is you have this import statement at the beginning of your code, import astropy.units as u or whatever other alias you want to use. I typically use u just because it's just one letter and it's pretty simple. And then you can assign units to your variables. So an example for how this might work is working with lengths. So let's say we define length 1 to be 1 meter. So how we do that is we do length 1 equals 1 times this AstroPy unit. So in this case, we're working with meters. So we do u.m. So AstroPy then interprets this as the unit meter. So kind of all the notation about what a unit is called in AstroPy can be found on its documentation, which you can just really easily Google. And it includes a whole bunch of different units. So let's say we wanted to define a length 2 in centimeters, 2 centimeters. So here it's the same notation as before. Length 2 is equal to 2 times u.cm. So our length 1's 1 meter, our length 2 is 2 centimeters. And then we just add the two lengths together. So big L is equal to length 1 plus length 2. And then if we just call L, we don't have to, convert one of the values to meters or one of the values to centimeters. AstroPy does it for us, and we get 1.02 meters. So this is a pretty simple example, but it kind of goes to show you how powerful AstroPy can be, and you just don't really have to keep track of those pesky units. So a little bit more about units in AstroPy. You can easily convert AstroPy quantities into different units. So the example that I have here, suppose you have some time in hours, right? I have t_hour is equal to 10.34 times u.hour, right? So 10.34 hours. And let's say I wanted to get this value into seconds, right? It would be kind of annoying to have to do this by hand. You could do it, but it's just annoying. So I can define some other variable. I can do t_s is equal to time in hours. And then to convert to a new unit, you use .to. So .to, parentheses, whatever units you want to convert to. So in this case, I want to convert my hours, my time in hours, to a time in seconds. So I do .to u.s. And then if I call this TS variable that I just defined, I get my 10.34 hours in seconds. Something else I wanted to note about AstroPy quantities is that sometimes like functions or plotting will be kind of annoying in dealing with them. It'll just like not know how to interpret it sometimes. So to get like the value, like the numerical value of some AstroPy quantity, you can do your variable name dot value, and that'll just return it to you in like a float. So it won't be like an AstroPy like object anymore. It's just like a number. Cool. So that's kind of a quick rundown of AstroPy units. Does anyone have any questions about this? Okay. Oh, okay. I don't think these are the updated slides. Let me see if I can refresh maybe. Okay, here we go. Awesome. Okay, so now I want you all to try using AstroPy yourself. So what happens if you try and convert 12 parsecs to hours using AstroPy? And then also, what happens if you try and convert 12 parsecs to meters with AstroPy? So I'll give you all a couple minutes to try this out and maybe discuss with the people around you what you're getting. If you're having any like errors like downloading AstroPy itself, just raise your hand and I can come over and help you. Yeah, when you've attempted both of these questions, just give me a thumbs up so I can kind of gauge where everyone's at. Okay, does anyone want to share what happens when you try and convert 12 parsecs to hours with AstroPi? Yeah. Yeah, so what does the error say? Yeah, so basically what AstroPi will tell you when you try and do this, it'll say, hey, parsecs is a length you're trying to convert to a time. You can't do that, and it won't let you do that. So this is kind of a silly example, right? But I think it's kind of useful when you're dealing with like equations and quantities. You can like try and convert to some unit that you know, like let's say you have some equation and you know that it's an equation for force, or at least you think it should be. You can try and convert whatever quantity you get to like a Newton or something. And if it's not actually a force, AstroPi will spit some error at you saying like, this is actually the units of this quantity. It's not actually the unit that you think it is. So I think it's kind of useful. How about if you try and convert 12 parsecs to meters? Did anyone try that one? Yeah, so if we were to try this ourselves, I can open up a new terminal window and zoom in, type out Python, import astropy.units as u. So I want to convert 12 parsecs to meters. So here I would do 12 times u.pc. So that's how AstroPi interprets this unit parsec. And then this .2 notation. Oh, that key doesn't work. Okay, ignore that part. 12 times u.pc 2, right, we're converting to a new unit, u.m. And if we run that, we get 3.7 times 10 to the 17 meters, which is a crazy big number. So that's kind of an example of how you can convert different units with AstroPi. Right, and just so I show you everything, if I try and do 2 or 12 times UPC to U dot, what did I say, hours, it raises an error and it says PC length and H time are non-convertible. Awesome. Okay, and then the last thing I kind of want to discuss before I hand it off is constants with AstroPi. So in science, there's lots of really important constants that we deal with, the Stefan-Boltzmann constant, the gravitational constant, et cetera, and they all have these like kind of confusing units and lots of decimal places, but you can load them in directly with like all of their different decimal places with AstroPi. So you don't have to like copy paste or anything like that. So we import this a similar way as we do astropy.units, but here instead it's import astropy.constants as, and you can use con or whatever other alias you want to use. And then you can just call from that package whatever unit you want to access. So in this case, I can define G, right, the gravitational constant, by doing G equals con.g. And that'll give me, this crazy, number with tons of decimal places that's important, but is confusing to remember. And to look up all the different constants that AstroPi kind of knows, you can look it up on its documentation and it'll give you like a huge table of all the different names of all the different constants. So pretty cool stuff. Awesome. And then I'll hand it off to Raphael.
All right, yeah, so AstroPy is super cool with the units and the constants, but it's also super cool because it can help us do astrophysics. So yeah, like depending what classes y'all have taken, astrophysical objects in the sky are specified by certain coordinates like right ascension and declination, which you can see the right ascension is essentially how far east or west it is from its position at the vernal equinox, which is in 5 days now. It's the spring equinox or whatever you want to call it. And then you can also specify the location of some object by its declination, which is how basically high or low it is relative to the north and south pole. Now, these are interesting coordinates, but if we have a telescope or something and we want to point it and it's not automated how to do that, we need to do something to convert coordinates so that we can point a telescope at a certain object. So basically what we want to convert to is some latitude and longitude like we have on Earth so that we can sort of literally point our telescope at those coordinates and see the object we want to see. So AstroPy is super useful for this because we can import this module called SkyCoord, and in SkyCoord we can put in some right ascension and declination like I was just talking about, as well as the distance away that it is basically. And then you can transform that into, for example, galactic coordinates, which is the latitude and longitude relative to our own galaxy, or even azimuth and altitude, where azimuth is just how far on the Earth's equator, if the Earth is a 360-degree circle, how far are we from the equator or the GMT Greenwich point. So this is all super complicated coordinate transformations, but the point is that you can use this to get the coordinates, and we pointed the telescope on the roof of Campbell Hall here using AstroPy at the Crab Nebula, which is an object in the sky, a nebula, I think a couple parsecs away. And we were able to use AstroPy in order to convert the right ascension and declination into sort of a azimuth and altitude that we can actually configure the telescope to point at. So yeah, I mean, it's just basically using the SkyCoord, looking up how to convert things. We'll go over this in a demo so it's a little more clear. But yeah, there's not that much to it necessarily. You just have to make sure you're in this ICRS frame, which just means you're in a standard frame in which the right ascension and declination are defined relative to a spring equinox of a certain year, basically. But yeah, besides coordinates, which we'll go over more in the demo, there's also tables, which are super useful. Obviously, you can use pandas, you can use NumPy load text, but AstroPy also has a way for you to import tables, which can be really useful when you're looking at, for example, isochrones. If you ever take Astro 160 or anything like that, AstroPy basically has all these capabilities for importing, loading data, plotting it, especially if you start to look at data that has astrophysical coordinates. It can become really useful because you can immediately do conversions and transformations right then and there, essentially. So yeah, so basically AstroPy, especially the coordinate transformation, I think is sort of a learn by doing thing. So we're not going to go over the cosmology. This is not updated because yeah, basically you can make plots of different distances in the universe based on the dominant factor, whether it's matter, radiation, or dark matter, but that's sort of more astrophysical stuff. The utility of it comes in the coordinate transformation and the constants mainly. So we'll go over that in the demo, which Annie will go over.
All right. So in this demo, we're going to be going over more about units and constants. So of course, the first thing we want to do is import astropy.units as you, just to make things easier. And the same thing with astropy.constants. So in the next cell, we're going to be talking about the gravitational force equation. And if you remember, that's F equals gmm over r squared. So in this case, if we want to write out the gravitational constant, all we have to do is c dot g, because g is already saved using AstroPy. And that's also true for the mass of the sun and the mass of the earth. So for the mass of the sun, we just have c dot m underscore sun. And for the mass of the earth, that's c dot m underscore earth. And for the distance between the sun and the earth, that's 1 AU. So all you have to do is write 1 times u dot AU. And to set everything up, like I said before, it's F equals gmm over r squared. So we multiply by g and the mass of the sun, the mass of the earth, divide by r squared. And this is going to give you units. Yeah, do you have a question? Yeah. Is this better? Okay. So this is going to give you kind of weird units. So I converted this to newtons, and that's just .2 u .n. And then that'll give you the result there. So it's very big number, right? And now for the next part, I'm going to be talking about the Hubble constant. Does anyone know what this is? No? Well, the Hubble constant is like an expression of the rate of the expansion of the universe. And this is, again, in kind of weird units, but it's in kilometers per second per megaparsec. So that's like speed per distance. Megaparsecs is like even bigger, right? So this is going to be 71 kilometers per megaparsec times seconds. And once you have that value, now we can use another equation. And this one is referring to the distance, not the distance, the speed that like a galaxy or something similar to that is traveling in the universe. And that's the Hubble constant times the distance from you to the object. So that's just written as d. So in this case, I just said d equal to 10 megaparsecs. So we'd be like really, really far away from this object, right? And then to find the velocity, you just multiply the Hubble constant that I found earlier by d, and you get a value of 710 kilometers per second. Now, say if we want to find the age of the universe, there's another formula for that. That's the Hubble time, which sometimes is written as TH, equals 1 over h naught. And you can take that value, and then if you just do 1 over h naught, again, the units are going to be kind of weird, but because everything is written out correctly, all you have to do is .to of u .year. So then we get the Hubble time of 1.37 times 10 to the 10th. So that's around 14 billion years. And now we're going to be talking about something pretty cool. This will be very helpful for any of you who are doing astro research in the future. First of all, I'm going to talk a bit about FITS files. Does anyone know what that is? Yes. Yeah, you can use it for spectroscopy. You can use it for imaging, any sort of astro data related things. That's what we use FITS files for. So it's very, very powerful file and very useful in astro research specifically. So if we want to download a FITS file, again, we're going to be using AstroPy. So to do that, we want to do from astropy.utils.data, and we import download file, which is a method from AstroPy. And then from astropy.io, we import FITS. So that'll help you with downloading the data. And I just imported pyplot, plt, matplotlib stuff here, so we can plot the data. So the first thing here, to get our image, I just set it as image file, and you use the function download file, which is from AstroPy. And then you just take the link of whichever website you're using. So I just found this one, and to specify which file you want, you just put that here. So mine was horsehead.fits. And then you just set the cache equal to true. And what that does is it like saves the data from the website. So if you want to run this again, it'll be easier to run. Okay, so now we have our image file, but we need to get all of the image data. So what we do there is we do fits.getData of the image file. And now that we have the data, we can plot it. And in this case, because it's going to be a 2D, we're going to use plt.imshow instead of plt.plot. So that's going to be plt.imshow of the image data. And I just set my color map equal to magma because I thought it looked pretty, but that can be whatever you want, right? And in this case, I just wanted to see what the dimensions of my data would look like. So I did image data.shape, and that was 893, 891. So basically a square shape, right? And of course, you want to have a title. So I did plt.title, and I made that Horsehead Nebula and nice big font size, and included the color bar. So this is what it looks like. Very pretty stuff. Yeah, that's it. Does anyone have any questions? Yes?
When you use show, the size is not the same, right? So I guess you can plug even though the size is not the same for the two things.
Yeah, because it has like two different values. So say like you're looking at one of the pixels, the one that's like 893, 891, that's just going to be like one pixel value, and then that has like a color value attached to it.
But there's actually like 3 axes.
Yeah, there's 3 here. It's like the pixels going vertically, horizontally, and then like the value that it's given that's shown with the colors. Any other questions? Okay.
Yeah, so really, well, yeah, I was gonna talk a little bit also about coordinate transformation. So I was gonna show you all the Crab Nebula coordinates in coordinates on Earth, basically, but also to show the utility of also what Claire and her resources she posted the other day. Does anyone have some astrophysical object they like or are interested in that we could get the coordinates for and transform? If anyone, yeah. Okay, yeah. So just to show, you could go, I mean, Orion Nebula is famous enough, I think, where it'll just tell me, yeah. So basically it'll tell me you can just Google it. You could also use, if it was more vague or lesser known object, you could go to Simbad on Claire's resources and put in the object name and it would tell you the exact coordinates. So basically it tells me that the right ascension is 5 hours, 35 minutes, 17 seconds. So the way that right ascension and declination are given are actually sort of in hours, where you have the right ascension is in 24 hours, and so is the declination, so that basically it's in terms of the time of day to an extent. But basically you can convert this to a degree by saying like, this is just going to be equal to 5 hours, 35 minutes, 17 seconds. So 5 point whatever 35 divided by 60 is, that's like, let's just say 0.58, and then for the declination, it's going to be -5, 23, 27.99. So if you say 24 roughly divided by 60, it's 0.4. So you could just say this is already almost there, and then this is -5.4. So you just put in the coordinates right here. I'm just defining them. And then you plug them in, and then basically here you import units as you, like Isla said. You can import time, you import the modules for the coordinates and to get the altitude and azimuth. And then you can also import Earth location. That Earth location and time thing is basically so that you can specify where you are, because obviously where you are matters if you're looking at something in the sky. So what we do is we put in C as our coordinates. So we say sky chord RA equals the right ascension I put in above times degree. The declination is the declination above times degree in the ICRS frame. Then you can just immediately print C dot galactic. So you can get the galactic coordinates just by doing C dot galactic with AstroPi. And then in order to get an altitude and azimuth, or a latitude and longitude, essentially, you have to specify where you are. So in order to do that, I use this Earth location module in which you can specify your latitude and your longitude. To be clear, this is just Berkeley, like I just looked up these values. And the height at Campbell Hall were roughly 122 meters above sea level. So I multiply by U dot M and U dot meters. I put in the time. Here it's very important you put the time in GMT time, which is Greenwich Meridian time. So that's 8 hours ahead of us. So right now it's no longer this time, it's 11:38 because it's 3:38 now. And then I can say C alt as is C dot transform to, and then use this altitude and azimuth module and the time and location that I put in order to get the galactic coordinates and current altitude and azimuth. So basically what this does is, like, literally if we had a telescope right here, we could put down a compass, find 230, then find what's 32 degrees off the ground, point it there, and that'd be the Orion Nebula. Like, so on the roof right now, we have a telescope like I was talking about. And for one of the labs in Astro, we're pointing at the Crab Nebula that I was talking about earlier for 12 hours. So we use while loops so that while we're within the time we want to run for, we just repeatedly make transformations, because the coordinates actually change a lot during the course of the day because obviously the Earth is rotating, the sun is rotating. So yeah, but basically the astroply can just keep updating our coordinates and we can keep looking at one object on the sky for an entire day or for an hour or for a minute, whatever you want basically. But the point is that just with Python and just with the Jupyter notebook, you could point at an object and basically get an image even if you had a way to run a telescope through here and look at it as a FITS file, like you could find an image like this. And we'll be talking a little bit more about FITS files probably later with research. But yeah, does anyone have any questions about coordinate transformations and stuff like that? Well, yeah, I guess in that case, that's the demo. I mean, yeah, if anyone has any questions, let me know. I guess we can have everyone go back into their groups and work for another 15, 20 minutes on the proposals for Friday. And that's, yeah. Sorry?
This demo is not posted.
Oh, it's not, yeah, I'll post it right now. Yeah. So yeah, you guys can use it. Yeah. But yeah, just to show you, like, it's kind of interesting. Like if we say it's literally what, 30 minutes later, the coordinates changed by, what was that, 23 degrees already. So yeah, stuff moves a lot is the point. But this astroply can keep updating no matter what if you give it a range of times, for example. But yeah, we'll post this and yeah. Let's get into the same groups, I guess, the way we did it last time and the time before, and let us know if you have any questions.
People seem to be celebrating.
Maybe you should just tell them it's blind. Yeah, I'll just give it.
And obvious is a little image. How many of it is like, well, I'm just thinking two is manageable. I certainly it's not how failure work. Because it's
Oh, yeah.
However, it looks like
The paper that we're is really long. You're the second or third, right?
yeah, like, so it's not really
Yeah. Okay, fine.
universal part.
It's like the same like that. Yeah, I learned a lot. I feel like I learned, yeah. It helped me read. I read papers better. What is this?
And they're like, give us 10 minutes to find it. No, yeah, so I'll just, I.
I didn't. It's setting up to add a table and then it had like a timeline, but I didn't do that. Yeah, that's something you could,
Yeah.
like.
The homework for actual part is still difficult. The one that James
Crazy
put
after
himself. Yeah, the milk, like the raw, like, yeah.
That was arguable.
Yeah, you should have given the guest license.
I know, that's what I kept telling you. I think we need to empty slot. What I guess or something. Anything. We don't know what's gonna be.
I don't need it.
Or research. What is?
I think I just ran out of stuff. Like you doing this entire course, what?
Wait, what?
Yeah.
I check
Let us present the paper. Present your paper. I mean, you Zoom.
We don't need to.
There's one person on Zoom, but there.
It's not our fault. Just, yeah. Oh, for the originality? Yeah. I don't want to wreck this.
Someone white lemonade.
Oh, that sucks. The capacitors, but I feel like
I think this is better.
yeah. Yeah. But it's still bad because you have to look at the numbers. Yeah.
Yeah.
Yeah. How's 100B?
I always want 11B. I'd love to do this.
It's not the phone.
Not the Delta, not Delta call. The Delta call.
Okay, I mean that's 4 delta functions. Yeah.
Oh, yeah, I heard that it's like 4 projects and that's it. It's like the entire class.
Yeah.
Okay. That gives me a better idea. No, I heard from someone else. Don't teach me. So worse than 11A.
No, I think it's worse. I think it's worse.
Maybe it's because I did it. Yeah, I know. Did you do it last
The
time?
tricky says it's easy. Why you do it? Oh, you did it last.
I did it. Because I took 11A over the summer and it was rough. It was real bad.
And you've been
Well, yeah. I mean, I wasn't anyways, but like. Yeah. Oh, really? That sounds great, but like that's not it's hell.
Oh, yeah, sorry about that, yeah.
I can manage that. 4 hours every day in a while. Oh, 4 hours in a while. It's just like no.
I think Brian and Benjamin
Yeah,
merge with their group,
okay,
but Brian's also not sure because he doesn't know what they're doing.
okay.
He said he would think about it, and then I should let you know it in the class.
Who is their group?
So it's group 2.
Oh, okay,
2v5.
yeah,
And I think they said Joshua has never shown up to class, but he texts occasionally. But he hasn't actually worked on anything.
okay.
He'll just say stuff.
Mhm. Yeah,
Good enough.
yeah.
I have the 7 weeks of it. I didn't do well in that class. I'm sorry.
Oh, yeah, yeah.
I forget those.
EWST. I'm good. No, I don't want to try too many.
I think Emily knows.
Okay.
It's from 2013.
Yeah, for you guys, for everyone on Zoom, if you want to join or text your group members about whatever, as long as you're in contact with them, it's all good. Let me know if you have any questions.
I don't know what's like outside. So yeah. Oh, in backyard. Oh, that's good. Front yard. No, it's front yard. Oh, wait. Oh my God. That's so cool. I got it. Yeah, and also like so like a 3D orbiting each other and the light. Maybe we can just do the 3D. Do you want to do something? I don't know. Yeah, you're adding it's like like having some sort of particular or do we want to just what's the I don't know Turkey is it's like you can just